Hello, and welcome to section 6.1 on inverse functions. Recall that a function f is an assignment to each element in a set A, a single element in a set B. A is called the domain of f, and B is called the range of f. We want to reverse this procedure. In other words, go backwards. We wish to assign to each element in the set B an element in the set A in such a way that it is compatible with the original assignments given by the function f. The natural way to do this is by choosing an element of B and seeing what element of A was originally assigned to it under f. This will be the assignment that will be defined to be the inverse function denoted by f inverse. But first, we note that there is some ambiguity for our choices. To remove the ambiguity, we make the following definition. A function f is one-to-one, or injective, if f of A does not equal f of B whenever A does not equal B. In other words, the function never takes the same value twice. The following figures show some examples. This concept can be easily visualized graphically. A function is one-to-one if and only if no horizontal line intersects its graph more than once. This is called the horizontal line test. The figure on the left shows a function that passes the horizontal line test. The figure on the right shows a function that fails it. We are now ready to formally define an inverse function. Suppose that f is one-to-one with domain A and range B. Then the inverse function has domain B and range A and is defined by f inverse of y equals x if and only if f of x equals y for all y in B. An immediate consequence of the definition are the following equations, called cancellation equations. F inverse of f of x equals x, and f of f inverse of y equals y for all x in A and y in B. At this point, let us mention a common notation error. F inverse of x is not the same as 1 over f of x. We now describe the procedure for finding the formula of an inverse function. Here are the steps. 1. We write y equal to f of x. 2. We solve for x in terms of y, if possible. And 3. We express f inverse as a function of x by interchanging x and y. The result should be y equal to f inverse of x. Let's do an example. Given f of x equal to 4x minus 1 divided by 2x plus 3, find f inverse. We follow the above steps. 1. We write y equal to 4x minus 1 divided by 2x plus 3. Next, we solve for x in terms of y. 2x plus 3 times y equals 4x minus 1. And so, 2xy plus 3y equals 4x minus 1. Moving the terms with x's on one side of the equation, we get 2xy minus 4x equals negative 1 minus 3y. Factoring gives x times 2y minus 4 equals negative 1 minus 3y. And finally, solving for x, we get x is equal to negative 1 minus 3y divided by 2y minus 4. In the final step, we interchange x and y, getting y is equal to negative 1 minus 3x divided by 2x minus 4, which is equal to f inverse of x. We now wish to study more properties of inverse functions. We first study what the graph of f inverse looks like in relation to the graph of f. Recall, by the definition of inverse function, f of A equals B if and only if f inverse of B equals A. In particular, AB is on the graph of f if and only if BA is on the graph of f inverse. Observe that the line y equals x is the perpendicular bisector of the isosceles triangle formed by the points AB, BA, and 0, 0. Thus, it follows that the graph of f inverse is obtained by reflecting the graph of f along the line y equal to x. Let's do another example. If f of x equals x cubed, then find a formula for f inverse and graph it. Y equals x cubed if and only if x is equal to the third root of y. So f inverse of x equals the third root of x. We now obtain the graph of f inverse by reflecting the graph of f of x equal to x cubed along the line y equal to x. Note that we do this piece by piece. We divide the graph of f of x equal to x cubed into subarcs along points where the graph of f of x intersects the line y equal to x. We then reflect each of these subarcs along the line y equal to x. Now, as we are in a calculus course, we are interested in doing calculus with various functions, so we wish to compute derivatives. A natural question is, can we somehow compute the derivative of an inverse function in terms of the derivative of the original function? The following theorem answers this question. The inverse function theorem says that 1, if f is 1-to-1 and continuous, then so is its inverse, and 2, if f is 1-to-1 and differentiable, and f prime of f inverse of a does not equal 0, then f inverse is differentiable at a, and f inverse prime of a is equal to 1 over f prime of f inverse of a. We omit the formal proof of the theorem, but we build intuition via the following figure. Note that the point A is in the range of f, and since f is 1-to-1, there is a unique point B that maps to A, i.e. f of b equals a. Hence the point b comma a is on the graph of f, and thus a comma b is on the graph of f inverse, as f inverse of a equals b. Since f is differentiable, it has a tangent line at the point b comma a, and hence the tangent line to the graph of f inverse at a comma b is obtained by reflecting the tangent line to the graph of f at the point b comma a about the line y equals x. Thus we compute f inverse prime of a is equal to delta x over delta y, which is equal to 1 over delta y divided by delta x, which is equal to 1 over f prime of b, which is equal to 1 over f prime of f inverse of a. Let's do another example. Find f inverse prime of a if f of x is equal to x cubed plus 3 sine of x plus 2 cosine of x, and a is equal to 2. To solve this, note that the inverse function theorem tells us that f inverse prime of 2 is equal to 1 over f prime of f inverse of 2. Thus we need two pieces of information: the derivative f prime of x and the value of the inverse function f inverse of 2. We easily compute the derivative to be f prime of x is equal to 3x squared plus 3 cosine of x minus 2 sine of x. Now what about f inverse of 2? To compute this, you should be asking yourself the following question. At what value of x does f of x equal 2? In other words, what maps to 2 under f? So one needs to solve the equation f of x equal to x cubed plus 3 sine of x plus 2 cosine of x is equal to 2. The obvious solution is x equals 0. So f of 0 equals 2, and hence f inverse of 2 equals 0. So now we compute f inverse prime of 2 is equal to 1 over f prime of f inverse of 2, which is equal to 1 over f prime of 0, which is equal to 1/3.